Hello friends, welcome to my YouTube channel. I hope everything is going well with you. Today I am going to discuss a problem from number theory, and the title of my video, as you can see here, is this expression a square plus b square divided by 1 plus ab is a perfect square if it is an integer. That means if 1 plus ab divides a square plus b square, where a and b are positive integers. N stands for set of natural numbers, that is positive integers. So our problem is, if a and b are two positive integers such that 1 plus ab divides a square plus b square, then the quotient a square plus b square divided by 1 plus ab is the square of an integer. In other words, if the expression is an integer for some positive integers a and b, then it is a perfect square. Okay. Some of the possible scenarios when this expression is an integer is given as follows. If the positive integers a and b are so chosen that b is equal to a cube, of course by symmetry if a equal to b cube also will work, then this expression is an integer. You can readily check it. Another situation is, if a and b are so chosen that a equal to t cube and b equal to t times t to the power 4 minus 1 for some positive integer t, then also it is an integer. Okay. And again by symmetry, if b equal to t cube and a equal to t times t to the power 4 minus 1 for some positive integer t, this will be an integer. Our methodology is this one. In order to solve this problem, we are going to use the principle of descent on maximum of a and b. This principle of descent is actually quite similar to the principle of mathematical induction. So let us see how it is done. So let us put n equal to maximum of ab, where a and b are positive integers. If n equal to 1, then since a and b are already positive integers, it follows that a must be equal to b must be equal to 1. Okay. If maximum value is 1, then each of them must be 1. And so this quantity is equal to 1, which is of course a square. Assume that the problem has been solved for all pairs of positive integers a and b such that the maximum value of a and b is strictly less than k. K is some positive integer. Let a square plus b square divided by 1 plus ab be an integer for some positive integer a and b with maximum value of a and b equal to k. So our assumption is that this is an integer if maximum value of a and b is less than k, and now we are assuming that our assumption is that the problem has been solved. That means this expression is a perfect square for all positive integers a and b such that maximum value of a and b is strictly less than k. And now we are assuming that it is an integer for some positive integer a and b with maximum value of a and b equal to k. We are going to show that this is a perfect square. So we put q equal to this quantity a square plus b square divided by 1 plus ab. Notice that if a equal to 1 or if a equal to b, then we have a equal to b equal to 1. This is because when a equal to 1, our a square plus b square divided by 1 plus ab becomes this one, 1 plus b square 1 plus b divided by 1 plus b. Okay, and this can be written as numerator can be written like this, 1 plus b square minus twice b, and denominator is as it is. Now this quantity is given to be an integer, so this is in n set of natural number, positive integers. So since this is an integer, so 1 plus b divides numerator, but this part of the numerator is already divisible by 1 plus b. Therefore, this part will also be divisible by 1 plus b. But 1 plus b and b are co-prime to each other, so 1 plus b must divide 2, and therefore b must be equal to 1. So, if a equal to 1, b is also equal to 1. And for a equal to b, the situation is this one. Our expression a square plus b square divided by 1 plus ab becomes this. And this is given to be an integer. We have assumed that this is an integer. So, this denominator divides numerator, but 1 plus a square is co-prime to a square. So, 1 plus a square divides 2. So, a square must be 1. So, a must be 1. So, therefore, if a equal to 1 or a equal to b, then we have a equal to b equal to 1. So, we can assume without any loss that 1 is strictly less than a and a is strictly less than b. Okay. Thus, we have k equal to maximum of a and b, which is of course already we have put k equal to we have already taken ab such that maximum of ab is k. But here a and b, according to our assumption, a is less than b, therefore the maximum is b. So it means k is equal to b. Now our aim is what? Our aim is we now wish to find a non-negative integer c less than b such that this q, which is originally equal to a square plus b square divided by 1 plus ab, now it becomes a square plus c square divided by 1 plus ac, the same q. Okay. So we wish to find a non-negative integer c which is less than b, strictly less than b, such that this expression holds. And that will actually finish the job. Why? Because if c happens to be 0, then this q becomes a square, which is a square. And if c happens to be positive, then we can apply the principle of descent to conclude that q is a square, because maximum of a and c is strictly less than b. Our c is strictly less than b, a is already less than b, therefore maximum is strictly less than b, and b is actually equal to k. That means this maximum is less than k. So we have this expression where c is less than k, and our principle of descent assumption, basic assumption of principle of descent says that our expression, that means our problem is solved when maximum of ab is less than k. That means we have assumed that a square plus b square divided by 1 plus ab, if it is an integer with maximum of ab less than k, then it is a perfect square. So using that principle, this problem will be solved if c is greater than 0. Therefore, our only aim is now to accomplish this aim. Now, we make an observation that every integer c less than b satisfies the following implications. That means if q equal to this one, then q is also equal to this one. Why? And conversely also, if q is equal to this expression, then q is equal to this one. Why? Because q is also equal to a square plus b square divided by 1 plus ab. Therefore, numerator here a square plus b square is equal to q times 1 plus ab, and here also numerator a square plus c square equal to q times 1 plus ac. So difference of numerator if you take, that means a square plus b square minus a square plus c square, that will be equal to q times 1 plus ab minus q times 1 plus ac. Therefore, if you divide the numerator, difference of numerator by difference of denominator, you will get q. So q will be equal to a square plus b square minus a square minus plus c square. So it will be b square minus c square divided by q times 1 plus ab 1 plus ab minus 1 plus ac. Okay. So this will be ab a b minus c, and here we have already taken c to be less than b, therefore this is meaningful. B minus c is not 0. Okay. So we can cancel b minus c. So we get q equal to b plus c divided by a. So this observation we make here. This suggests that we may now choose our c to be equal to, from here, aq minus b. So if we choose c to be equal to aq minus b, and if we can show that this particular c is less than b, then this expression also will hold. And if we can show that c is also greater than or equal to 0, then our aim also will be fulfilled. So we work with c equal to aq minus b. Note that our q is actually equal to a square plus b square divided by 1 plus ab. So this is less than, if you remove this one, that means if you reduce the denominator, the value of the quotient will be increased. So it will be a square plus b square divided by ab. So it will be strictly greater. Okay, this quantity will be bigger. And this one divide throughout by ab. So first term will be a by b, second term will be b by a. So q is less than this quantity. Now multiply throughout by a. So aq will be less than a square by b, and this will give you just b. So a square by b, b. And a is less than b, so this quantity is less than b square by b, b is b. And this is b plus b, so it is twice b. So what we have done is aq is less than twice b. Shift one b from right side to left side, so we get aq minus b, which is actually our c. It is strictly less than twice b minus b, that is b. So that means what we have shown is that c is strictly less than b. So one part is done. Therefore, from the observation, now we can apply the observation. Observation says what? That if c is less than b, then this implication holds, two-way implication. And our c, choice of c says that this condition is satisfied, this equality is satisfied. And c already we have proved that it is less than b. Therefore, this equality also holds. So, therefore, by that observation we have q equal to a square plus c square by 1 plus ac. But q is originally equal to a square plus b square divided by 1 plus ab, and it is greater than 0 because ab are positive integers. So this q is greater than 0 means denominator is also greater than 0. Numerator is already positive. So denominator is greater than 0. So if denominator is greater than 0, this means AC is non-negative, because AC plus 1 is positive, means AC is non-negative. And A is already positive, therefore C must be non-negative. So therefore C is greater than or equal to 0. So we have actually accomplished our aim. Our aim was that we want to find a non-negative integer C less than B, such that this equal to this expression holds, and that we have achieved. Okay, and we have already mentioned that once our aim is achieved, then the result of the problem is solved. Therefore, our problem here is rigid. Yeah. Hence, the problem is solved. So, hope you have enjoyed it. Thanks for watching.